In this video, I'll talk about follow-up procedures that you can do after you completed your factorial ANOVA. So let's go back to our example of a 3x3 ANOVA where we have a two-way ANOVA because we have two independent variables, a 3x3 factorial ANOVA. We have animal type and we have condition. And we saw that we need to include main effects. There's two comparisons there, hams to cats and cats to dogs. That's encoded in some dummy variable. There's some main effect here, two dummy variables, control to music and music to book. And therefore comparisons in the interaction effect that are included as well as parameters in the dummy variables. In this case, these four comparisons. Now, that's nice. If we do this, then the model will run and these parameters are somewhere included. We don't really see them in the output anymore if we do the ANOVA button, but we see them in the output if we do the linear regression button in JAS. But what if we don't care about these specific comparisons? So what if we don't want to compare control to music or music to book? We want to do some other comparison. Like maybe instead we want to compare control to the overall effect of music and book, and then a second comparison, compare these two. That's also two comparisons. We could also encode that as dummy variables. That's fine. You'll get significance values from that, so that's possible in principle. It's a bit hard to think about how you encode the dummy variables, but maybe that's what we want to do. So the parameters in the model are estimated together with their standard errors. Standard errors is the variability around the parameter, the estimate of the variability around the parameter. This means that if you run ANOVA in JAS, it does a linear regression model with default dummy encoding. Doesn't really matter what it is because we're not going to do the dummy encoding manually, but you just have to realize there's some dummy encoding below it, and that gives us parameters with standard errors. And now because of this, we can obtain t-statistics and significance test, which is nice. We can do significance testing for these dummy variables in principle. The interpretation of these depends on the coding of the dummy variables used, and you don't get to choose it in JAS because JAS will do the dummy variable coding for you already. Luckily, it turns out that we really don't have to care about the dummy coding as all. We don't have to care about this. In ANOVA, JAS doesn't even report the regression coefficients associated with dummy variables. JAS does this, but then it doesn't actually report these parameters. It is in there, it doesn't report it. And this is because there is something simpler we can use called contrast. And basically what a contrast does is it transforms the regression parameters and the significance into the exact effects we're interested in. So a contrast is a way to specify a specific hypothesis about the difference between groups. We get a significance value associated with it, and this is how you really interpret it. It's basically some form of mix-up, transformation of the information in dummy variables to whatever we're interested in. So because of that, we shouldn't actually test more contrast than we have parameters. And that's important. Basically, if we run our model, let's say our 3x3 design, right? It had how many parameters? 9, including an intercept. We shouldn't, so 8 really on the differences between groups. We shouldn't try to do more tests than 8 on comparisons between the groups because we don't have more information in the model. You could get it out in JAS, you can actually specify 10 if you want. But the problem is that there's some overlap. Those are actually based on only 8 significance values. So the significance is slightly off, which is a bit problematic. A contrast is a set of numbers that should encode a specific hypothesis about differences between groups. And in JAS there's a button for it. I'll show that later as well in the video. The contrast should contain a number for each group you're comparing, and the sum of these numbers should be 0. This makes it actually look very similar to a dummy variable, and that's confusing. Some textbooks even have it wrong. They think contrasts are dummy variables, but they're not, and you can show it mathematically. So it's just confusing. And just remember that dummy variables are really explained so that you have an idea about how you can include categorical variables in a regression model. But the encoding, that's not something you actually do manually. You let JAS handle that because contrasts allow you to specify whatever you're interested in. In the contrast, you compare the average of the group with positive weights to the average of the groups with negative weights. So step 1, you choose 2 sets of groups you want to compare. The contrast weights for the other group should become 0. Step 2, in the first set, you make the weights 1 divided by the number of groups. In the second set, you make the weights -1 divided by the number of groups in that set. And that's it. That's how you specify a contrast. These 3 steps. So let's say we want to compare cats to dogs and we don't care about hamsters. We would specify contrast with a 0 for hamster, a 1 for dogs, and a -1 for cats. And so here in this case, I'm encoding a contrast. I put a 0 for control, which means that in this comparison, we don't care about control. Control is not playing a role. Okay. Anything at 0 is not included in the comparison of this contrast. In this case, we encode music as 1 and reading as -1, which means that we are comparing the difference between music and reading. And how you can see it is really just this. You add the means multiplied by the contrast. If you have a balanced group, and this works especially well. So here, right, we type 0 times the mean of control. So control it just drops out. Then we have 1 times the mean of music plus -1 times the mean of reading. And that leads to the mean of music minus the mean of reading. If that difference is 0, then these 2 groups are the same. They have the same mean. That allows us to do a comparison between music and reading. Right, and maybe that's something we planned beforehand. We wanted to say, okay, I'm going to do an ANOVA. If the main effect is significant, I'm going to compare specifically the music and the reading conditions. And we do that with a contrast. We can specify, okay, we planned this beforehand. We're going to specify this contrast. We already planned which contrast we're going to specify. Then we just add it in JASP and we get the p-value. I call this contrast C1. Let's do a new contrast, C2. So what am I doing here? I'm comparing control to music and reading. Okay, so I specify for control -1 and I specify for music and reading half, so that the sum of this is again 0. So basically what contrast am I specifying? The average of the mean and reading conditions minus the control condition. If that equals 0, then we know that the control condition on average does not differ from the experimental conditions. Right, and that allows us to test the effect between the control condition and both experimental conditions at the same time. Assuming equal sample sizes, we're going to assume that you have roughly equal sample sizes. You should have that if you randomize. If not, yeah, you can read more about it in the textbook. I'm not going to explain it in detail, but roughly this works. This is quite robust if you have about equal sample size, which you probably should have. Okay, JASP also allows you to specify custom contrast to specify the exact hypothesis you want to test, but also, so you can do this in JASP, you can specify these contrasts, but also in default contrast that you might hear about. You can specify in JASP, okay, I want simple contrast. If you do simple contrast, then there are 2 contrasts specified. In this case, for this main effect, we have only 3 groups, but we can only do 2 contrasts. Okay. Here they're compared to the first group, so you can do control against music and control against reading. And there's something called a Helmert contrast. And here each group is compared to the mean effect of all subsequent groups. So we first compare control. That's a C1. Compares control to the average of music and reading. You see that here. This one compared to that one. And in C2, music doesn't play a role anymore, and we look at the difference here. A Helmert contrast is actually what we did here. Because we did it in the other way around, but it's the same idea. You can also define contexts for interactions. So in the interactions menu, you'll get specify contrast for all possible groups. In this case, 9, 3 by 3. And we can specify, for example, I want to compare these 2. I say in my follow procedure, I'm actually interested in seeing if the hamsters are different from the music condition hamsters, different from the control condition hamsters. I can specify that. I just add -1 to hamster and 1 to the control and 1 to music. So it sums to 1, 0. And the rest doesn't play a role. They're all zeros. All these are dropped out. right? And we're only left with a comparison between these two groups. Let's take a look in JASP on what contrast looks like. So we have contrast here, this button. And we see here for the two main effects, the interaction effect, we can specify our contrast. We can do these helmet ones, for example, that will do the comparisons. In this case, it's only for two levels, so we don't really need this because we already have the main effect. But we can also specify custom one. In this case, maybe we want to see, do people rate the food court one on average higher as AI than the other ones, regardless if the picture is actually AI or not. And we can specify that contrast and we get a significance value out of that. In this case, this is actually significant, right? Because we see it here. People rated the food court one much more as AI, even though if it was real or regardless if it was real or AI. We can also specify one for the interaction effect. So maybe here we want to particularly look at the red panda one. And we want to say, okay, give me the significance of this comparison here for the red panda group between the AI and the real one. And I get the significance here. This one here. We get a significant effect as well as significant difference. Now, an important thing to note is that this comparison here between two groups, right? So here in this case, we compare AI to real in only the red panda condition. We could also do that by just removing every other photo type and doing an independent sample t-test, but we would get a bit of a different result if we do that. In this case, residual degrees of freedom is still in line with the residual degrees of freedom of the final model, and we use all the information we have in the model for the standard error estimate, so it is a bit different. This is a bit more of a precise estimation. Another thing we can do is a simple main effects analysis, and here we look at one variable for a specific level of another variable. It basically is like performing a one-way ANOVA for each level of the second variable. For example, we can test if there's an effect on condition for a particular animal, like hamsters. Simple effects are useful when you have a specific hypothesis about one particular group. Maybe there's only one group you're really interested in, and your follow-up hypothesis about that group. You want to see, is there actually a difference in this group? Right. Now, it's a little bit different than cutting out the other groups and doing a one-way ANOVA. We do have the other groups, which help for the standard error estimate. So you get a bit of a more precise estimate. So it's not exactly the same as a one-way ANOVA for each level, but it's comparable to that. So let's look in JASP again. We have here our analysis. Let's get rid of this contrast here. Let's get rid of this one here. We see simple main effects button here. We go down, and what can we do? Well, for example, we can put a type moderator factor and simple effects factor here, photo. And we see here a table where we have two different f-tests. These are basically two different one-way ANOVAs, except that the residual degrees of freedom is still 40 from the final model. So here we look for the AI ones, for the real ones. These are actually different photos, right? So maybe you want to look at it like this. And see, okay, is there an effect in the AI ones? Is there an effect in the real ones? Interestingly enough, the AI ones don't have a significant main effect anymore for the distance between the three photos. So all three photos are judged as equally plausible to be generated by AI, apparently. It's only in the real photos that we see this effect here. And that's because this one here, right? People thought that food court photo was really AI generated, even though it's not. Right, so that means that this line here, this white line, this increase is not really significant. We don't actually see a significant difference between the groups in these particular AI condition. All right, now the final thing that you can do are post hoc tests. Now, post hoc tests are basically every possible combination of groups we can do a t-test for. Right, so we have in this case 9 groups, right? 3 by 3. So we can do for every possible combination of those groups a t-test to see which ones are exactly different. Now, that only makes sense to do if the interaction is significant, otherwise there's no reason to look at the group level. So basically, the test will simply compare all possible combinations of groups using t-tests with the pooled standard error, so it's not exactly the same, it's running separate t-tests, but it's very similar. Now, this number can quickly become very large, right? So for n-g groups, in this case we have 9 groups. The number is 9 times 8 divided by 2. That's a very large number already. And you expect that 5% of these tests are different by chance alone, are significant by chance alone. Right? So if you perform at least 20 tests, you should expect that one of them is going to be significant by chance alone. Now, if you followed the PL2132 course, I let you throw a lot of dice, and the dice are different colors and at different tutorial groups. And it turned out that if you mine the data long enough, you get some significant difference between the dice throws from one group compared to another group, or from like one color compared to another color. I generated a paper by Dr. Hamster, Professor Hamster, basically claiming that the two colors are significantly different from each other, even though it's purely based on chance. What I did there, I just looked like a lot. I did a lot of tests, and I just looked at one so significant, and I cherry picked that, and I wrote a paper about that. Absolutely bad practice to do, right? And that's what we want to avoid. But yeah, that's important to note. If you do a lot of tests, some of them are going to be significant by chance alone. So in post hoc tests, we do actually too many tests. We do more tests than we're technically allowed to do. If you look at the number of parameters in the model, right? We only have, in this case, 8 degrees of freedom. We have 2 for the main effect, 2 for the other main effect, so that's 4, and we have 4, right? So 8. Technically, we should only do 8 comparisons, but we're doing more, way more, right? So that's problematic. And also we're like searching for something. And we're doing it post hoc. Post hoc means we do it after the results are in and the results are known, right? So this is something you really only do after you, or you're supposed to do only after you got your data, your results, and you want to explore more things that are happening in your data. And that's really an important thing here. If you want to explore that, and then maybe if you find like a group differences and you want to write a paper about that, then you should take into account that you're doing multiple comparisons. Because of this, when we do post hoc tests, we control for multiple comparisons. We control for the fact that we expect that 5% of these tests are going to be significant by chance alone. The way that we do that is, so here we see, right? So all possible comparisons is a lot. In this case, 36 possible comparisons. That's a lot. We expect at least one of them or 1.5 of them to be significant. So we want to control for that. So when using post hoc comparisons, we compare all possible groups in an exploratory manner. We want to make sure that we limit the chance of finding any significant result to alpha. Any significant result. We want to make sure that out of all these comparisons, we only want to get a significant result if any of them, suppose they're all 0, we only want to get one significant result 5% of the times out of all of them. Right. So there's some commonly used adjustment that we can do. The most common one is the Bonferroni correction, and it simply multiplies the p-value by the number of tests. In this case, the p-value is multiplied by 36, right? P bonf equals p times 36. Now that makes it much harder to be below 0.05. The Tukey HSD is a bit less strict, and that's more commonly used. I'm not going to explain in detail how it works, but it still increases the p-value by a substantial amount. These work best when group sizes are about equal. And this is an important thing. This is the most important thing actually here. We do this because post hoc testing is by definition exploratory. We do this after we have the data and we did our analysis, and now we want to explore what else is happening in our data. We do not do post hoc testing to test something that we planned beforehand. Now many people do this, and many people will say that you should do this, and they say, okay, you first do your ANOVA and then you do your post hoc test. Most people that write papers do it like that. But technically, we shouldn't do that because we have contrasts and simple effects for that purpose already. If you had a comparison between two groups in mind, right, before you run your analysis, you should have specified a contrast, and you could have already specified it beforehand. Or you could have even gotten that via the post hoc test, but then not adjust for multiple comparison, but the contrast would have been a more elegant solution. By default, JAS will adjust the p-value in the post hoc test for the multiple comparison. And it's a good thing it does that because, yeah, it prevents Dr. Hamster type of situations. But at the same time, that's a bit of a downside if you already had the plan beforehand to compare only two groups, right? So maybe your plan was never to do all these comparisons, right? maybe your plan was always from the beginning on to only compare the control and the music condition of hamsters. If that's the case, you don't need to adjust for 36 or 35 other tests you would not have done. Right? And that's why we can do the contrast or the simple effect, in this case it's contrast. And we don't have to adjust the p-value because we already planned that analysis beforehand. Now if instead you say, okay, I wasn't planning on this particular test, I just want to look at general, exploratively, what's happening, and then report which group differed significantly. Then we do post-hoc test with multiple comparison. And that's a really important point. All right. Now, some more follow-up questions. Shouldn't you also adjust for multiple comparisons when using f-test, simple effects, or contrasts? A Bonferroni correction is always easy to apply, so you could do it if you want. But if you adjust the p-value, you also limit your power to detect real effects. So ideally you don't. And most commonly, researchers do not adjust p-values for planned hypotheses, but they do adjust p-values for unplanned hypotheses, explorations. So for your f-tests in your ANOVA, you get 3 of them, right? The main effect one, the main effect another one, and interaction. Typically you don't adjust that p-value because you were already planning on looking at those 3 effects, and then it's fine. Right? Your hypothesis already is about, okay, expect the main effect, expect the main effect, expect interaction. Then it's fine. But you could consider adjusting p-values of the post-hoc test manually to a different number of tests if you want. That's something that people don't often do. But indeed, maybe there were certain things you would not care about. Maybe you really only want to explore a certain subset of all the possible tests. It's possible, but it's something that's not commonly done. Most importantly, carefully plan your hypothesis before the start of analysis. Plan how you will adjust your p-values for exploratory post-hoc tests. And be clear in your reporting which tests were planned and which were exploratory. This is the most important part. Very important for psychological research. You should state in your report very clearly what your plan was beforehand and what you did after you found the data and saw the data. All right, let's take a look at JASP again for the post-hoc test. So here we have post-hoc test. And let's say we want to compare all the groups. So we can actually just add also one level, right? So we can say type, we get only the difference between the 2 types. In this case, it's only 1, so there's actually no multiple comparisons there. But let's do all the possible combinations. We add the interaction effect here. We get all the possible combinations for all the possible groups. We had a 2x3 design. So how many comparisons we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 comparisons. So this p-value is adjusted for 15, and that's why all these p-values are so high, including 1. Now you see here that JASP doesn't even allow you to not correct the p-value. Or does it? See? It doesn't even give you p-value. There's no option in here for getting a non-adjusted p-value. Right. So if your plan was to compare, let's say, these 2 groups with each other and nothing else, yeah, this is not the place to be, right? You could do that in the contrast menu. That's where you do that. This is for exploratory search, seeing what's different. But we can add some things here. We can see, in this case, I would do the Bonferroni and the Tukey. There are some other options here, but let's do these. See, the Bonferroni is much more conservative and lots of 1s. And we see that only this difference here, AI red panda versus real red panda, significant. AI food court versus, no, not that one, real dog walk versus AI dog. Red panda is also significant. Bit of a weird combination, but yeah, we see which are still significant. Right, that's it for this video.